So we actually have quite a bit to cover today, and we'll just see how far we get. I'm not sure if we're going to get all the way through what I have on the board or not. Maybe not. We'll just see. So we talked about gas and gas, right? And I think that's about where people started to pack up because we're almost out of time. We talked about gas and liquid. Okay. So then I think the next one we were ready for then was the liquid in liquid, okay? An example of a liquid in liquid solution is vinegar, okay? Vinegar is a mixture of acetic acid, which is a liquid, and water, which is also a liquid, obviously. So you mix those two together, and you're going to end up getting vinegar. Yes?
Is acetic acid, is that what vinegar can smell, or is that something else?
Yeah, that's the acetic acid is what gives it vinegar its smell. So you guys, in the last lab we did with the lead acetate, you remember that stuff, those few drops that you had to put in of that really strong solution to clarify it? Did you notice a smell coming from that, maybe? Like a vinegar type smell, okay? That's acetic acid. That was really concentrated acetic acid. Way more concentrated than vinegar. If you drank that stuff, it would eat your throat. But vinegar is only about 5%, okay? And so that's not nearly as strong of an acid. It's much more dilute, so that's okay, all right? But that's where the vinegar smell comes from, is that acetic acid. All right, a solid and liquid. This is the one we're probably most familiar with when we're talking about solutions. Salt water is a good example of a solid dissolved in a liquid. Give me another example of a solid dissolved in a liquid.
Sugar and water.
Okay, so sugar and when would we put sugar in water?
Kool-Aid.
Okay, so Kool-Aid's an example. When else might we put sugar in water? It's way more popular down south than it is here. Well, okay, lemonade.
Soda pop.
Sweet tea, right? Okay, we'll come back to sweet tea because that becomes important later. But yeah, sweet tea. That's, again, when I was in Texas, sweet tea was a big deal. Here in Missouri, not so much.
They drink Arizona tea?
No, I think that's not quite sweet enough for the Texans. Sweet tea, the idea in sweet tea is to get as much sugar dissolved in your tea as is humanly possible, right?
That's so gross. So much sugar. That confused me.
So all of those, okay, anytime you have sugar dissolved in water, that's an example of that solid and liquid solution, okay? You can also have a liquid in a solid, which is weird. We don't have as much experience with this, okay? Dental amalgam. This is basically a filling, okay? Now, how would you like to put this in your mouth? Silver is solvent, the mercury is the solute. Mercury is not so great for your brain. So they're getting away from putting the mercury in, but there are a lot of people, if your parents have a filling of any sort, they probably have mercury in their mouth right now. Because that's what they used to use, okay? Please do not do that. I know that was the chair saying please don't tip it, not that noise. Okay, and then another one, solid and solid. You guys ever heard of alloys before? Have we talked about alloys this year? I don't know why my voice got so high just then. Sorry. So, solid and solid, okay, that's an alloy. So, like if you mix two metals together, and a lot of times the reason you would do that is to make the metals stronger or to give them better properties than they originally have. So steel it's a very important example of this, okay? Almost everything that's built industrially is made out of steel. Now, steel is mostly iron, but what's the problem with iron?
It rusts.
It rusts, okay? And it's a little less hard than we want it to be, okay? So there are a couple of things you can mix in with iron that give it more desirable properties, okay? If you put carbon in with iron, that makes steel, and it's a much stronger, harder material at that point because the carbon basically just slips into some of the holes between the iron atoms and just reinforces it and makes it stronger, okay? There are other things you can mix with iron, like chromium. Chromium does not rust. So if you mix chromium with iron, any guess what that's called? What kind of steel that might be?
What do you say?
It doesn't rust. Stainless steel, right? Okay, so chromium mixed with iron, you get stainless steel. So there are a lot of really important alloys you can make by mixing two solids together. Yes, ma'am.
Like a solute and a solvent?
Okay, so solute and solvent, just to remind you on that. Solute, remember the Kool-Aid example that we talked about on Friday. Solute is the thing that's present in the lowest amount. It's the thing being dissolved. Okay? So like the sugar in the Kool-Aid example would be the solute. Okay? The solvent is the thing that there's more of, or the thing that's doing the dissolving. Okay? So solvent would be the water in the Kool-Aid example. All right? Now, here, when you've got something like a solid in solid solution, it's a little bit tricky to figure out what's the solvent, what's the solute. Let's have everyone go back to the seats they're supposed to be in. Thank you. Okay, so the reason we call iron the solvent here is because we're only putting in a little bit of carbon, right? It's mostly iron, okay? So that's the solvent. There's more of that. There's less of the carbon, all right? Okay, so here's a little question for you. Coke lists its ingredients: carbonated water, high fructose corn syrup, and or sucrose. The good Coke, the throwback Coke, is sucrose. It's just sugar, not high fructose corn syrup. Caramel color, phosphoric acid, natural flavors, and caffeine. So the question is, what is the solvent, or what are the solvents in this case?
Carbonated water, right?
Okay. I would step back even from saying carbonated water.
Water.
I would say just water is the solvent, right? What does carbonated mean?
It has carbon.
It has specifically carbon dioxide in it. You remember that? They push a whole bunch of carbon dioxide into the soda, and that's what gives it the bubbles. Okay? So the carbon dioxide is not the solvent. It's just the water that's the solvent. Okay? So then what about the solute or solutes? Okay, sucrose or the high fructose corn syrup. We just talked about the carbon dioxide, right? What else? Caffeine. Basically everything else, right? Okay, everything but the water is going to be the solute. So all these things that are dissolved in the water, those are the solutes. The solvent is the water. That's the thing doing the dissolving. Does that make sense? Okay, so that's how you tell the difference between solute and solvent. All right, now we need to talk about concentration. So when you drink your Kool-Aid, and let's say you go home after school today and you decide, you know what, my Kool-Aid is never concentrated enough. All right? What are you going to do? You're going to less water or more sugar, right? One of those two. So that there needs to be more of the solute for the amount of solvent. Okay? So when you drink that and there's a lot of sugar dissolved in that water, how are you going to describe it?
Sugary.
That's really sugary. What's another way you might describe it? That's really sweet. You might say, ooh, that's really strong. Okay, like if you have something that's really concentrated. So those are some qualitative terms that we can use, just some descriptions. Now, what are you going to say if maybe there's not enough sugar dissolved in the water?
Bitter.
So that's watery. I wouldn't say bitter necessarily. Water's not bitter. Okay, gross or disgusting. You might say flat, right, if you're talking about the carbonation. Okay.
Unsweet.
Unsweet. Okay. I liked watery. Have any of you ever used the word...
Down.
Okay, watered down. Have any of you ever used the word dilute for something like that before? You heard of that word? You probably wouldn't. I mean, that's probably not a normal vocabulary word for you at this point, but it will be soon, okay? Dilute just means there's not very much of the solute, okay? If it's really concentrated, that means there's a lot of the solute, okay? So that's kind of how we describe it in qualitative terms, okay? But in this class, do you think it's good enough for you to look at a solution and say, ooh, that's really concentrated, or ooh, that's really dilute? Or, like everything else in this class, are we going to use numbers? probably going to use numbers, right? Okay, so we need something more quantitative, something that involves numbers to measure the concentration of a solution. Okay? So to create a solution, you've got to have a solute dissolved in a solvent. We know that at this point. This is a solution, by the way. It's not just water. There's ions dissolved in here, right? Well, because I got it from the tap, because I reused this after I... But I think it originally came with ions in it. Okay, chemists represent how much solute is dissolved in solution by indicating the concentration, okay? So again, we can say, ooh, that's really concentrated, or that's really dilute, but instead of just using those descriptive words, we're going to use numbers. So concentration is a measure of how much solute is dissolved in a specific amount of solvent or solution. There are a lot of different ways to measure concentration. Okay, you need to be familiar with several of them because they're going to come up again if any of you take any more science classes after this. Especially in biology, a lot of times these ways of measuring concentration come up. You did, but a lot of people go on to take anatomy or AP bio or even, I think, in forensics or zoology, botany, you might need these things. AP, environmental science, all of these things, you need to know how to measure concentration. Okay, so, oh, sorry, were you not done? Yes, you need to know concentration for the rocket fuel. That is rocket science, but if you want to be, yeah, anyway. Okay, so the more solute dissolved in a solution equals a higher concentration. The less solute dissolved in a solution equals a lower concentration. You might put next to lower concentration, you might put dilute, just so that we remember that word, okay? Dilute means there's not as much, or there's not very much solute dissolved in the solution. There are 6 ways to express concentration. That's probably not true. There are probably more than 6. We're going to talk about 6 right now. Percent by mass, that one we're going to learn how to do calculations with. Molality, that one we're not going to learn how to do calculations with. Molality, yeah, it is weird. It's molality, yep. Percent by volume, we're going to do calculations with. Mole fraction, we're not going to do calculations with.
Pretty much never equals percent.
Molarity, we are going to do calculations with. ppm or ppb, anybody know what that stands for?
Percent
Per mole.
Okay, that's a good guess.
per mole.
It's actually parts per million or parts per billion, okay? Now, when would that particular measure of concentration be important? Parts per million, parts per billion. In other words, that's like when you have really, really, really small concentrations of something. When would that be important, maybe? Okay, maybe when we're talking about molecules. What about if we're talking about levels of toxicity? Like in a lake or something like that? How toxic is the level of mercury in a lake? Or how toxic is the level of mercury in the fish that you're eating? You guys know that? If and when some of you get pregnant, you are going to be told by your doctor not to eat certain types of fish. Okay? The reason for that is because certain types of fish, the bigger ones, have a high amount of mercury built up in their systems because the little fish get some mercury in them, and then the big fish eat a bunch of the little fish, and the mercury just keeps building up and building up. And when you eat one of those big fish, those mercury levels are too high, and it can damage a fetus. So you have to be careful. Your doctor will tell you to stay away from certain types of fish. Small fish, probably okay. The big fish, not so much. Well, I'm not saying that it's not hurting the fish either, okay? But if we eat that fish with the mercury in it, then it can build up to toxic levels in us. And it's eating that bigger fish is probably not going to hurt you, but it might hurt the small thing growing inside of you, if that makes sense, okay? What's that?
No.
Well, that's possible, but that's not where the mercury is coming from, probably. I don't know about that. I'd have to. You might be right. I'd have to look into that. So that's where parts per million or parts per billion might come into play. There are certain things. Listen up. There are certain toxins, certain poisons that are toxic on the parts per billion level. So if you have one molecule in a billion molecules of that particular toxin, it can damage you. It can hurt you. It can cause brain damage. It can kill you, even in some instances. So this becomes very important when we're talking about toxins. All right? But we're not going to cover that in here either. If you do AP Environmental Science, you'll probably end up talking about parts per million, parts per billion. Maybe in AP Bio, maybe in forensics, because in forensics you might talk about some different poisons and toxins that could kill somebody. So that's an important measurement there. But for chemistry, we're going to stick with the ones on the left side here. Percent by mass, percent by volume, molarity. Okay? Those are the ones you're going to learn how to calculate. So let's start with percent by mass and percent by volume. Concentration expressed as a percent. It's just a ratio of solute to solvent. Okay? So you're going to have to keep in mind as we go through these, what's the solute, what's the solvent, and then we're going to make a ratio between those two. Okay? So percent by mass usually refers to solids dissolved in liquids. So if you've got salt water, in the example of salt water, what's the solute?
Salt.
The salt, right? What's the solvent? Water. Okay. The ratio of solute mass to the mass of the entire solution is expressed as a percentage for mass percent. Okay? So you find out what's the mass of the solute, in other words, what's the mass of the salt, and then what's the mass of the entire saltwater solution, and you set that up as a ratio. Okay? Here's the equation. Do you guys have to write this down, or is it already there? You got it already? Okay. So percent by mass is mass of solute divided by mass of solution times 100. All right, let's practice. Well, there's the equation again. In order to maintain a sodium chloride concentration similar to ocean water, an aquarium must contain 3.6 grams of NaCl per 100 grams of water. What's the percent by mass of NaCl in the solution? Really? We probably should have picked a better problem than that. Oh, okay. No, I changed my mind. I like that. I like that question. What's the percentage? Now, those of you who are really looking at this, you're going to say probably right off the bat, oh, 3.6%, right?
Yeah.
Because 3.6 grams of NaCl and 100 grams of water. Is that right?
Yeah.
Why not? Because we have to be thinking about what's the solute and what's the solution, right? Okay, so here's the, what's the solute here? It's the NaCl, right? Sodium chloride, okay. I actually like this problem now that I noticed the trick, because we're kind of setting you up for that. So the solute is 3.6, okay? Well, why did I not leave myself more room here? 3.6 grams is our solute divided by the mass of our solution. What's the mass of our solution?
Oh,
103.6, right? Because the solution is the solute and the solvent put together. Okay? See the trick there? So 103.6 grams, and then you times that by 100.
Is that grams of NaCl?
You can label this as grams of NaCl up here if you want to. And then this one would be the grams of salt water, because it's the entire solution, right? 3.47 sounds about right. Oops. Is that the right number, sig figs? 3.47? Oh, yeah, okay. let me do this. Because I don't like one sig fig in our answers. That's never good, right? And there would only be one if we did it this way. So actually, technically, when you're adding these two to, never mind. Just pretend there's a decimal point there, okay? All right, so no, I need this to be 100.0 for this to work. Because then when you add the 100.0 to the 3.6, then it's 103.6, and you can use that number down here. Otherwise, you'd have to round this to 104, right? But we'll say it's 100.0 grams, okay? So how many sig figs should we have in our answer here? 2 because of the 3.6, right? There's only 2 there, so 3.5%, which is actually pretty close to the 3.6% that we originally thought it was going to be, right? But it's a little bit different. Okay, everybody all right with that? That's not too bad, is it? Okay. What is the solute? What is the solvent? What is the mass of the solution? We actually figured all those things out already. So, moving on. Percent by volume. That describes solutions in which solute and solvent are both liquids. Okay, so that's usually when you would do a percent by volume solution. So based on what we've talked about so far, give me an example of a time when we would use a percent by volume. Do you remember the liquid-liquid solution that we talked about? Vinegar, right? Okay, so vinegar, when they tell you the percentage on the vinegar bottles, I think they tell you it's about 5%. Okay? That's a percent by volume. That means that 5% of the volume of what's in that acetic acid, or in that vinegar bottle, is acetic acid, and the other 95% is water. Does that make sense? Okay, so figuring out percent by volume, volume of solute divided by volume of solution. So this is really very similar to the mass percentage thing. It's just volume instead of mass times 100. All right, practice problem here. What is the percent by volume of 25 milliliters of methanol in 75 milliliters of water? Anybody want to take a stab at this without even doing a calculation? Oh yeah, we got to figure out which one is solute, which one is solvent, right? Now they're both liquids, so how do we decide which one is solute and which one is solvent?
The water, I feel like it's always the solvent.
Water's usually the solvent, okay? Not always. But why would water be the solvent in this case? Okay, so it says the methanol is in water, so that's a big hint. What's our other big hint here? There's more water, right? Remember, the solvent is the one that there is more of, okay? So on this one, we're just going to take 25 milliliters divided by 75 milliliters times 100, right? Oh, you guys caught me. Good job. Divided by what? 100. Yeah, and that's why someone, you know, if you're looking at this closely enough, you could probably figure this one out in your head. Because this basically just cancels with this, right? So you end up with 25%. That's all there is to that. Pretty easy, right? Of course, we can make it harder. We probably will a little bit. But that's how that works. Whoops. Okay, so we figured out what the solute and the solvent were. We figured out what the volume of the solution was. So, good job. All right. Another way to calculate concentration is molarity. Okay? Now, this is the one you're probably not familiar with at this point, I'm guessing. Anyone ever heard of molarity before? The only way that you might have is, well, I mean, you might have heard of it in your other science classes potentially. In biology, they don't use molarity quite as much as we do in chemistry. Chemistry, this is pretty much the one that we use most of the time. Okay? So where you may have heard it in this class is if I tell you the concentration of a solution back there, like I may have told you at one point this is 6 molar sodium hydroxide, or this is 12 molar hydrochloric acid, so don't get it on your skin, right? Because those are very high concentrations. So that's all based on molarity. So molarity is a very common one, like I said, especially in chemistry. And it's the number of moles of solute dissolved per liter of solution. Okay? So moles per liter is going to be the unit for molarity. That's your formula. It's already on your paper. Okay. Moles over liters. Now, be careful again, because this is moles of solute and this is liters of solution. Okay, so you just have to watch that. The units, you can say molar if you want for the units. It's technically moles per liter. You can also just write a big M. Okay? Any of those are acceptable for the units for molarity. You can also write moles over liters if you want to abbreviate this one, right? Okay. So let's do an example problem with molarity here. 100.5 milliliter IV solution contains, you guys know that's what IV stood for? Intravenous. Does that make sense, kind of? I mean, you're putting it into your veins. So it contains 5.10 grams of glucose, which is C6H12O6. What's the molarity of this solution? Oh, and they're even nice enough to give you the molar mass of glucose, 180.16 grams per mole. Well, okay, so things got a little bit more complicated here. Let's keep in mind the formula for molarity. What's the formula? Moles of solute over liters of solution. Okay, so what's our solute in this example? Okay, are we in agreement that glucose is the solute, the thing that's being dissolved? Okay, so that's our solute. Pretty much, yes. I can't think of an exception to that. Okay, so that's the solute. What's the solvent here? Yeah, the rest of the IV solution, right? So the solution is the solution. Kind of makes sense. Okay, yeah, so the problem here is we have grams of the solute, not moles of the solute, right? Yeah, but that's okay, because we have this. This will get us from grams to moles, won't it? And like I said, they were nice enough to go ahead and calculate the molar mass for you, so you didn't have to do it. So 5.10 grams of the glucose, C6H12O6. And then we know it's 180.16 grams in 1 mole. And that's going to give us a really small number. 0.0283. Okay, good job on the sig figs. And I'm just going to put, oh, no, never mind. I'm getting ahead of myself here. That's how many moles we have, right? Okay, so now what? Oh, yeah, because this needs to be liters of solution down here, not milliliters, right? That's another place where you guys are you're gonna forget that step often because it's easy to forget. For this unit, that's a conversion you really need to know. Okay, how many milliliters are there in a liter? 1,000, right? So just write that down somewhere on your notes, star it, say you need to know this, okay? In order to do all the molarity calculations that you do, or a lot of them, you're going to have to know the conversion. All right? So we've got 0.0283 moles of our solute divided by, oh, we didn't do the conversion yet, did we? 100.5 milliliters, 1 liter and 1,000 milliliters. So basically we divide by 1,000. Okay. Some of you are going to get to the point where you don't have to do this. You can just swing the decimal over 3 places in your head. Right. That's essentially what happens when you divide by 1,000. The decimal goes 1, 2, 3 places to the left. So then you're, yeah, it's good to check. 1,005 liters. Right? Everybody good with that? Okay. So there's your setup on that one. You're going to end up with a molarity of, everybody got it? Okay, which we're going to round to 0.282, right? 3 sig figs because of our, this number right here that we started with. So then, what is this? 0.282 what? Okay, you could say moles per liter. You could say molar. You could say big M. Okay, I usually label these with just a big M because I'm lazy and that's the fastest one. But you need to know what that means. You need to know that means moles per liter, right? All right, everybody good there? Yep. Can you not see that? Sorry, I'm too far down on the paper. And my stack is getting too high over here. It says 0.282. Whoops. Remember to make sure, yeah, we talked about that. Okay, here's another example. How many grams of NaOH are required to make a 500 milliliter solution with a concentration of 3.5 molar? We're kind of working backwards here, right? So remember, our equation, molarity equals moles of solute over liters of solution. But what do we have this time in the problem? We have the volume and we have the molarity, right? So we can use that to find the moles of the solute. Now what's the solute in this particular problem? We're in agreement there? NaOH is the solute. It's probably the thing being dissolved in the water, right? Okay, so that's our solute. And we know how much the solution we have, right? Okay, so I'm just going to set this up. 3.5 molar is equal to, we'll just say X for right now. That's basically what we're trying to find is the moles of the solute. Over 500? Okay, yeah, you got it. This is milliliters, right? So you have to convert that to liters. So again, if you're a little shaky on that still, just go ahead and set up your dimensional analysis. Milliliters on the bottom, liters on top. There are 1,000 milliliters in a liter, so okay, I need to divide. Okay. Another way to think about that, milliliters is smaller than liters, right? So if you end up deciding that there are 500,000 liters in 500 milliliters, does that sound right? No, because liters, that's a lot bigger, so you should have a smaller number that goes with that bigger unit, okay? All right, so we're going to divide by 1,000, which is going to give us 0.5. And actually, that's only 1 sig fig here, which is not my favorite thing in the world, but that's okay. So then we're going to multiply those two together, right, to solve for x. So x equals 0.5 times 3.5, which is going to give us 1.75. We'll round this in a minute, okay? 1.75 what? Grams? Okay, remember we're solving for this, right? Okay, so we just found the number of moles of NaOH. They're asking us for the number of grams of NaOH. Okay, so now what? Now we have to do, yeah, a little bit of more mass work here. 1.75 moles of NaOH. in, I promise. You already got that calculated? I'm just saying that because I don't want to do it right now. I'm getting 39.9969, which you could almost just round to 40. But especially since we're only going to have one sig fig in our final answer here. Yes, you're going to round that to 70. 70 what? 70 grams of NaOH. Because the 0.5 down here is only 1. So really, I shouldn't have, but you don't want to round too soon because we're doing another multiplication down here. So as long as you're just continuing with multiplication, I usually wait till the end to round.
So that one would have been 2.
Right. Yeah. But see, then if you round there, it kind of changes your final answer. So, okay, everybody good on that? I think that's where we're going to stop for today because the molar solution stuff is, yeah, probably so. I'm going to give you a worksheet here, and I need you to hear me on what parts of this worksheet to do and which parts not to do. So let me turn this off first. Yeah.